So in this example on triple integrals, we have to evaluate this triple integral z dv over the region E. And we are told that E is a solid tetrahedron bounded by the four planes. So x equals 0, y equals 0, and z equals 0, as well as x plus y plus z is 1. So these three, x equals 0, y equals 0, z equals 0, tells us that we are working in the first octant. And for triple integrals, whenever we evaluate triple integrals, we'll always draw two diagrams. One for the solid region E, over which we have the triple integral, and one for the coordinate plane onto which we make our projection. So let's first look at the region E, which will always be in 3 dimensions. So we can start with E. And as we said, we're dealing with the first octant, so we just have to draw this plane in the first octant. We can get the intercepts with the axes by making x, y, and z 0 respectively. So we find that we have something like this. And the intercepts with the axes will be 1, 1, and 1. So this is the plane that we're dealing with. Then the region E will be bound by this plane and the coordinate axes. So it's the region inside here. Then secondly, we want to draw the projection, and in this case we can project onto any one of the coordinate planes, such as the YZ plane or the XZ plane or the XY plane. So we can project onto the XY plane. And the second diagram, as we said, will always just be in 2 dimensions. So it's in the XY plane. And we're basically looking at this as our projection, this flat area in the XY plane, which is bound by the X and Y axes, as well as this line. So let's just draw the line. And we can see that the line also intersects the axes at 1 and 1. And of course, the equation of this line is just going to be y equals negative x plus 1. And we're looking at this region in the xy plane. Once we've drawn the 2 diagrams, we're going to proceed by always writing the solid region E, over which this triple integral is defined in terms of rectangular coordinates. So it's going to be this set, always of x, y, z. Then such that, now going to the coordinate plane onto which we're making our projection, in terms of a double integral, we can define this either as a type 1 region or a type 2 region. So I'm going to use a type 2 region, which is going to be a vertical arrow. So we're going to regard as x as being bound by numbers, and y we're going to regard as being bound by functions. So then x will be between 0 and 1. Y will be, we said we're using an upward arrow. So y will be bound by the x-axis, which is y0, and by this line, which is of course 1 minus x. And then z, looking at this diagram for E, clearly z goes from 0 to this plane that we've drawn over here. Now, just to go back to the equation of the plane, we can write this in the form z equals 1 minus x minus y. So we have stated E then in terms of rectangular coordinates. Now we are ready to set up the integral, the triple integral. Now, we know it's the integral of z dv. And this is a type 1 projection or a type 1 region in terms of triple integrals. So we know we're going to write dz first. Then over here, we need to insert dA. In other words, the region in the xy plane, and we said that x are bound by numbers, so and y is bound by functions. So we're going to write dy on the inside and then dx. Now we just write down the limits for the integral. Dx, the outer one, will be from 0 to 1. Then dy is from 0 to 1 minus x. And z is from 0 to 1 minus x minus y. Now, it should be clear that we don't have to use polar coordinates since we're dealing with a triangular region here and not a circle in the xy plane. So we can proceed to evaluate this as an iterated integral straight away. Then starting with z, it's going to be z squared over 2, evaluated from 0 to 1 minus x minus y. And then, of course, we still have dy dx. And we can pull out the half in front of the integral. And then just plugging in for z 1 minus x minus y. Of course, we needed a 2 here. So let's proceed to evaluate the integral. Now, the antiderivative of this will be 1 minus x minus y cubed divided by 3 and divided by the derivative of the inner function with respect to y. This, of course, is evaluated from 0 to 1 minus x. Now, in finding this antiderivative here, I've basically just used this rule. If I have a linear expression which I want to integrate and it's to the power n, then it's equal to ax plus b to the power n plus 1 divided by n plus 1, and also divided by the derivative of the inner function, which is a. We can pull out negative a third from here. Now I'm going to substitute in the upper limit for y. And then 0 for y. Of course, this will be cubed. And then plugging in 0 for y. All these terms will cancel here. And I'm going to pull out this negative so we can make this a positive here. And it's going to be the integral of 1 minus x cubed dx. Once again, finding the antiderivative using this rule, 1 minus x being a linear function or expression. It's going to be 1 minus x to the 4 divided by 4 and also divided by the derivative of 1 minus x. We can pull out negative a quarter. And of course, our limits of integration will be 0 to 1. Then plugging in 1, I'm going to get 0. Then plugging in 0, I'm going to get 1 to the 4, which is 1. And the final answer is 1 over 24. So example 4 will deal with triple integrals using cylindrical coordinates. Now, cylindrical coordinates is just a 3D equivalent of polar coordinates. So we have a point P with coordinates r, theta, and z, where r is the angle, or rather theta is the angle measured clockwise from the positive x-axis. R is just the radius, and z is this vertical height. Then we use the same set of x and y rectangular coordinates as for polar coordinates. So x is r cos theta, y is r sine theta, and then we're just adding that z is equal to z. We also still have x squared plus y squared is r squared, and tan theta is y over x. So the question now is, when do we use cylindrical coordinates to evaluate triple integrals with? Suppose E is a type 1 region. In other words, a region which we can project onto the xy plane conveniently. And let's say that projection onto the xy plane is described, or can conveniently be described, in polar coordinates. So let's say the region in the xy plane is a circle. And suppose f is continuous. And let's say the solid E is described by this set, where z is bounded by two functions, u1 and u2, in x and y. And d is given in polar coordinates. In other words, the projection onto the xy plane can be given in these coordinates, theta between alpha and beta, and r between two functions of theta, h1 and h2. So this is what the sketch should look like. We have the solid region E, we have u2 and u1 by which z is bounded, and then we have a projection onto the xy plane, and this is the area D. So this area, and we can see that r is bounded by the function h1 of theta and h2 of theta, whereas theta is bounded by constants alpha and beta. Now, we know that the triple integral, so the triple integral over the solid region E, in this case where it's a type 1 region, it will come out to this, where we have dz evaluated first. We have z1 equals, or z equals u1 and z equals u2, and the inner integral here, of course, will be the integral with respect to z. And we have dA on the outside, which could either be dx dy or dy dx, as we have done before. Then we can express a triple integral over the solid region E as this iterated integral. Now, theta goes from alpha and beta, from alpha to beta. R goes from H1 to H2. And Z goes from U1 to U2. Now, note that Z is a function of X and Y. And we've simply just replaced X and Y by R cos theta and R sin theta in U1 and U2. Then f of x, y, and z, x and y we've replaced with polar coordinates. Note that z remains z, because in cylindrical coordinates z equals z. Then also note that just like with polar coordinates, we need this magic factor of r, which is really the Jacobian of polar and also cylindrical coordinates. And we're evaluating z first, so we first need the dz, and then of course dr d theta. In example 4 it says, a solid E lies within the cylinder, x squared plus y squared is 1, below the plane z equals 4, but above the paraboloid z equals 1 minus x squared minus y squared. The density at any point is proportional to its distance. In other words, the distance from of the point from the axis of the cylinder. So basically from the origin. Find the mass of the solid. Now, I'd like to start by pointing out that one of the applications of triple integrals is that of the mass being equal to the triple integral over the region E. So the mass of a solid E is a triple integral over the solid region E of the density function. So of a function f of x, y, and z dv, where f, as we said, is basically the density function. Now, we can first find f of x, y, z. We know that the density at any point is proportional to the distance from the axis of the cylinder. So the density f of x, y, z is proportional. So it's equal to a constant. So it's proportional to the distance, which basically is x squared plus y squared using the distance formula. And the k here is just a constant, a proportionality constant. We want to express each of these functions in terms of cylindrical coordinates. So let's start with the cylinder. Now the cylinder's x squared plus y squared is 1. And we know that x squared plus y squared is r squared. So basically it's r squared equals 1. So that's the equation of the cylinder. Then looking at the paraboloid, let's find that in cylindrical coordinates. Here we can see it's going to be z equals 1 minus r squared. Right, now we can also draw the region, or we should draw it. So basically we have the cylinder with radius 1. Then we have the paraboloid. Now note that when z is 0, x squared plus y squared is 1. So we have a circle in the xy plane of radius 1. Then when x and y are both 0, z equals 1. So we know the paraboloid, the maximum height on the z-axis will be 1. And then we have the plane z equals 4. And we want the solid region bounded by the cylinder, the paraboloid below, and the plane above. So we're really looking at this region, the solid region. Now we can express E, the solid region, in terms of cylindrical coordinates. So it's going to be the set r theta z, such that theta in the xy plane, as we said, we have a circle here in the xy plane. So theta clearly goes from 0 to 2 pi. It's a circle of radius 1, so r goes from 0 to 1. And then z will go from the paraboloid below to this plane above. And we know that the paraboloid is 1 minus r squared. And the plane z equals 4. Now we can set up the triple integral, but before we actually do that, we can rewrite this density function in terms of cylindrical coordinates. We know that x squared plus y squared is r squared, so f is just going to be k times r. We can now set up the triple integral. The mass is the triple integral over the region E of the density function, which you know is k times the square root of x squared plus y squared. We're first expressing the triple integral in rectangular coordinates. Now we can express it in cylindrical coordinates. We saw that the square root of x squared plus y squared is just r. And then remember, we are projecting onto the xy plane, so we need z. And then we also need the magic factor, of course, which is r for cylindrical and polar coordinates. So this is just the Jacobian. And then we said we need dz first. Now, both theta and r are bound by numbers, so it doesn't matter which one is on the inside and which on the outside. So theta goes from 0 to 2 pi, r goes from 0 to 1, and z of course goes from 1 minus r squared to 4. Now, we can pull out the constant here, which is k. and we're left with r squared z dz dr d theta. Of course, it goes from 0 to 2 pi for theta, 0 to 1 for r, and z from 1 minus r squared to 4. Now we can continue evaluating this triple integral. We're first going to integrate with respect to z. And z goes from 1 minus r squared to 4. And we still have dr d theta. Now, I won't go right to the end here, but if you continue evaluating this integral, we end up with 12 pi k over 5 for the mass, where k is just a constant. Let's look at the last example on cylindrical coordinates. We are given this triple integral in rectangular coordinates. Now, we're first going to look at the xy plane. Now, the xy plane, or the region in the xy plane, is clearly given by the first two integrals. X goes from -2 to 2. Y goes from this function, which is a semicircle, or part of a circle, this part being the bottom half of the circle, and this one the top half. So we are clearly looking at a circle of radius 2. So x goes from -2 to 2. Y goes from the bottom half of the circle to the top half. Let's now look at the limits for z. We want to draw this region. We're going to need a sketch in 3D. Now, we're interested in what this looks like. Now, note that when z is 0, we have x squared plus y squared is 0. So in the xy plane, it's just going to be a point. Then, as x increases, or rather as z increases, we have circles with increasing radii. So something like this. Then also note that when y is 0, we have z equals x, which is a straight line in the zx plane. And in the same in the yz plane, when x is 0, we have z equals y. So another straight line in the zy plane. So really what we're looking at is a cone. Then if we put these two together, we see that it's a cone above the region, above the circle in the xy plane. In other words, a circle of radius 1, or rather radius 2. Now, if we extend the circle upwards, we know that x squared plus y squared equals 4. So then z equals 2. So we also have a plane in the plane z equals 2. So really we're looking at, if you note here, z goes from the cone to the plane z equals 2. In other words, we're dealing with the solid region inside the cone, extending from the xy plane to the plane z equals 2. Now, we can convert the equation of the cone to cylindrical coordinates, and of course, it's just going to be z is the square root of r squared, so z is r. Now we can express the triple integral over the region E of x squared plus y squared dv in terms of cylindrical coordinates. So I haven't written down the set E, which you should usually do, but theta obviously goes from 0 to 2 pi. Since we have a circle in the xy plane, r goes from 0 to 2. Now, z goes from the cone, which is r, to 2. And of course, x squared plus y squared is r squared. Then we also need the magic factor, which of course is r for cylindrical coordinates. And then of course, we have dz, because our projection is onto the xy plane, dz, dr, d theta. And we just evaluate this in the usual way.